Hold your hand up to the light for a moment. In the second it takes to read this line, about 100 trillion tiny particles pass straight through your palm, through your bones, through the earth beneath your feet, and out the far side of the planet, and not one of them so much as nudges an atom on the way. These are neutrinos, and when the physicist Wolfgang Pauli first dreamed one up in 1930, he was so certain it could never be caught that he apologized for inventing it. This is the story of that particle, the one that shouldn't leave a trace, and of how, almost a century later, CERN finally caught it in the act. We'll build it up slowly, one simple step at a time, starting with a single puzzle about a decaying atom. If quiet, careful science is your kind of late night, consider subscribing before we begin. So where did the missing energy go? Picture a single atom of a radioactive element, sitting quietly until, without warning, it changes. One of its neutrons turns into a proton, and in the same instant it flings out a fast electron. Physicists in the early 1900s could catch that electron and measure how much energy it carried. They expected every electron from the same kind of atom to come out with the same energy, the way every ball dropped from the same shelf hits the floor at the same speed. That is what made the measurement so strange. When James Chadwick looked carefully in 1914, he found no single energy at all. The electrons came out with a whole range of energies, from almost nothing up to a sharp ceiling, and most of them fell short of that ceiling. It was as if you dropped 1,000 identical balls, and they landed at 1,000 different speeds, none of them faster than a fixed limit, most of them slower. The books did not balance. Energy went into the decay, and less energy came out with the electron, and the difference had nowhere to go. For a while, some hoped the missing energy was hiding somewhere in the apparatus, lost to heat or leaks. So in 1927, two physicists named Charles Ellis and William Worcester built a careful test. They sealed a beta source inside a thick lead calorimeter, a device that traps and measures every scrap of heat released. If the missing energy was really there, escaping as some invisible radiation, the calorimeter would still catch it as warmth. It did not. The heat matched the average energy of the electrons, the smaller number, not the ceiling. The energy was not hiding. It was simply gone. This was not a small bookkeeping error. Conservation of energy was one of the deepest rules in all of physics that promised that energy is never created and never destroyed, only moved and transformed. Beta decay seemed to break that promise, over and over, in a way no one could explain. The measurements were clean, the instruments were sound, and still the energy vanished. The crisis reached the very top of the field. Niels Bohr, one of the founders of quantum theory, began to wonder aloud whether energy conservation might simply fail inside the atom. Perhaps he suggested the rule held only on average, across many decays, and any single decay was free to lose a little energy into nothing. It was a radical thought from a careful man, and it shows how serious the problem had become. To save the measurements, one of the pillars of physics might have to fall. Not everyone was ready to let it fall. Lise Meitner, who spent years measuring beta decay with great precision, kept confirming the continuous spread of energies without ever concluding that energy itself was lost. The spectrum was real. The question was what it meant. Either a bedrock law was broken, or something was carrying the missing energy away, something no detector had ever seen, something that slipped out of the atom and out of the laboratory without leaving the faintest mark. Hold on to that fork in the road, because everything ahead grows out of it. On one side stood the possibility that nature keeps loose books. On the other stood an invisible thief, a particle so faint that it could steal energy from every beta decay and never once trip an instrument. The first path led nowhere. The second led to a single letter, written by a troubled physicist who did not much like the idea he was about to propose. He would suggest the thief was real, and he would spend years worrying that no one could ever prove it. That letter is where the neutrino begins. In December of 1930, a group of physicists gathered in the German town of Tübingen to talk about radioactivity. Wolfgang Pauli, one of the sharpest minds in the field, could not attend. He was in Zurich, and by his own cheerful admission he did not want to miss a ball he was invited to that same week. So instead of coming in person, he sent a letter to be read aloud, and he opened it with a joke, addressing the assembled scientists as his dear radioactive ladies and gentlemen. The letter was playful in tone and serious in content. Pauli proposed a way out of the missing energy problem, and his way out was to invent a new particle. Suppose, he said, that when a nucleus undergoes beta decay, it does not only throw out an electron. Suppose it also throws out a second particle, one that carries no electric charge, one so light and so faint that it slips away unseen, taking the missing energy with it. The books would balance after all. The energy was never lost. It left in the pocket of a particle nobody could see. For this to work, the particle had to be a very particular kind of ghost. It had to be electrically neutral, so it would not tug on the charged plates and wires that detectors used. It had to be extremely light, lighter than the electron, perhaps with no mass at all, and it had to interact with matter so weakly that it could pass through the walls of any experiment and vanish into the room, the building, the sky. Pauli even named it, at first, the neutron, borrowing a word that would soon be taken by something else. Pauli knew he was on thin ice. Inventing a brand new particle just to patch a hole in the accounts was the kind of move careful physicists distrusted. You could explain almost anything if you were allowed to conjure invisible objects whenever the numbers went wrong. He felt the weight of that. In a remark that has followed the neutrino ever since, he confessed that he had done a terrible thing, that he had postulated a particle that could not be detected. To propose something in physics that no experiment could ever reach felt, to him, like breaking the rules of the game. That worry was not idle. By his own estimate, the particle would interact so rarely that catching even one might lie forever beyond human reach. He had solved the puzzle on paper, but the solution seemed to place itself out of view, permanently. It was a strange kind of victory, to rescue a law of physics with an object you feared could never be shown to exist. Pauli reportedly offered a case of champagne as a bet that the particle would never be caught. So certain was he that it lay out of reach. Still, the idea had a quiet power. It did not ask physics to abandon energy conservation. It asked physics to accept one more resident in the world, a faint and neutral thing that carried away what the electron left behind. Bohr's radical option, giving up the conservation law, now had a rival that was in some ways more modest, and in some ways stranger. Keep the law and accept a particle you may never touch. For a few years, the suggestion sat mostly unexamined, an intriguing footnote in letters and hallway conversations. Pauli himself was slow to publish it in full. The particle needed something his letter had not given it, a real theory of how beta decay works, a framework that could take this shy neutral object and place it inside the machinery of the atom. That framework would come from Rome, from a physicist who gave the particle both a proper name and a proper home in the laws of nature. The word neutron did not stay attached to Pauli's ghost for long. In 1932, the English physicist James Chadwick discovered a genuinely new particle inside the nucleus, neutral like Pauli's, but heavy, about as massive as a proton. That particle took the name neutron and kept it. Pauli's feather-light object needed a name of its own, and it got one in Rome, in the group around Enrico Fermi. Someone there, half joking, called it the neutrino, using an Italian ending that means the little neutral one. The little one, to set it apart from Chadwick's heavy neutron. The name stuck at once. Fermi did far more than rename it. In 1933 and 34, he built the first real theory of beta decay, and he built the neutrino into its foundations. In Fermi's picture, beta decay is not the simple ejection of an electron that was somehow waiting inside. It is a transformation. A neutron in the nucleus turns into a proton, and in that instant of change, two new particles are created together and fly out, an electron and a neutrino. They did not exist a moment before. They are made on the spot the way a spark is made when two wires touch. To make this work, Fermi had to propose something bold. The transformation, he said, is driven by a new force of nature, one that had never been named. It was not gravity, which is far too feeble to matter here. It was not electromagnetism, which pushes and pulls on charges. It was not the strong force that binds the nucleus together. It was a fourth force, acting only over incredibly short distances, and it was faint compared to the others. In time, it would be called the weak force, and the neutrino would turn out to be its favourite messenger, the one particle that feels this force and almost nothing else. Fermi's theory was quantitative, not just a story. It predicted the exact shape of the beta spectrum, the smooth curve of electron energies that had so puzzled everyone, and it predicted how that shape depended on the mass of the neutrino. When the calculations were compared to the measurements, they fit. The strange continuous spectrum was no longer a mystery. It was the natural signature of energy being shared in every possible proportion between the electron and its invisible companion. Sometimes the electron took most of the energy, sometimes the neutrino did. The ceiling everyone had measured was simply the case where the electron took nearly all of it. There is a small, telling detail in this history. When Fermi submitted his theory to the prestigious journal Nature, it was rejected. The editors judged it too remote from physical reality, too speculative to interest their readers. One of the most important papers of 20th century physics was turned away for being too strange. Fermi published it elsewhere, and he was reportedly stung enough by the reception that he turned his attention toward experiment for a while. The idea, of course, was right. With Fermi's work, the neutrino had grown up. It was no longer a desperate patch scribbled in a letter. It was a full member of a working theory, with a defined job, a governing force, and predictions that matched the data. Physicists now knew what the particle was supposed to be: a neutral, nearly massless thing that felt only the weakest of forces and slipped through matter almost without touching it. They could calculate its behaviour with real numbers, and yet, for all that progress, no one had seen one. The theory said the neutrino was everywhere that beta decay happened, which meant it was pouring out of every radioactive rock, every reactor to come, every star in the sky. The next question was brutally simple, and it would take more than 20 years to answer. If these particles are streaming through everything, how weakly do they really touch us, and could any machine on Earth ever be made sensitive enough to catch one in the act? To feel how faint the neutrino's touch really is, it helps to start with something solid. Imagine a block of lead, the dense grey metal used to shield against radiation. A single sheet of it, a few centimetres thick, will stop most of the dangerous rays that come off radioactive material. Lead is our picture of a wall that particles cannot get through. Now send neutrinos at it. To a neutrino, that thick protective wall is barely there. The reason lies in the weak force, the one force besides gravity that the neutrino feels. The weak force has an almost unimaginably short reach. Electromagnetism, by comparison, stretches across a room, across the space between the sun and your skin. The strong force, though short-ranged, is mighty within the nucleus. The weak force acts only across distances far smaller than a single proton, and even then it acts gently. A neutrino flying through matter is like a person walking across an empty stadium, where the atoms are scattered seats, and the neutrino only reacts if it strikes a target dead center, and even a direct hit is a soft one. Physicists measure this reluctance with a number called the cross-section, which you can picture as the effective size of the target each atom presents to the incoming particle. For most particles, that target is generous. For the neutrino, the target is fantastically tiny. The chance of a hit on any given atom is so small that a neutrino will typically sail past uncountable trillions of them, one after another, touching none. It is not that the neutrino is aimed carefully. It is that the door it must pass through is almost always closed. Here is the comparison people reach for, and it is worth sitting with. To have a fair chance of stopping a single neutrino from a nuclear reactor, you would need a wall of lead about 1 light-year thick. Not 1 meter, not 1 kilometer. A light-year, the distance light travels in a year, roughly 9.5 trillion kilometers, all of it solid lead. Only then would the odds of that one neutrino interacting climb to something like even. Every thinner wall, and every wall we could ever build, lets it through. This is why Pauli despaired. A particle that ignores a light year of lead is not a particle you catch by building a better detector in the usual sense. You cannot simply make the wall thicker or the shielding denser. The neutrino treats density as almost meaningless. Send it through the whole Earth, 8,000 kilometers of rock and iron core, and the overwhelming majority pass clean through and out the other side as if the planet were a faint mist. But look closely at that phrase, the overwhelming majority. It is not all of them. The cross-section is tiny, yet it is not zero. On rare occasions, a neutrino does strike an atomic nucleus squarely, and something happens. The weak force acts, particles are made or changed, and a trace appears. The trick, the whole trick, is that rarity times number can still be large. If the chance per neutrino is 1 in many trillions, but you have far more than trillions of neutrinos pouring through, then somewhere, sometimes, one of them will speak. That is the crack of light the hunters would eventually pry open. You cannot force a single neutrino to interact. What you can do is stand an enormous number of atoms in the path of an even more enormous flood of neutrinos and wait and watch for the vanishingly rare moment when one of them touches. To do that, you first need a source pouring out neutrinos in truly staggering numbers. As it happens, the greatest such source in our sky had been burning quietly overhead the whole time, 93 million miles away. Step outside on a clear day and turn your face to the sun, and you are standing in a wind you cannot feel. Along with the warmth and the light, the sun is spraying neutrinos across the solar system, and they arrive in numbers that are hard to hold in the mind. Through every square centimetre of your skin that faces the sun, roughly 65 billion solar neutrinos pass every single second. A patch the size of a thumbnail. 65 billion, each second streaming through. They come from the sun's core where the real engine runs. Deep in the centre, hydrogen nuclei are fusing into helium under crushing pressure and heat, and that fusion is what makes the sun shine. But fusion does not only make light. Each time the process turns one kind of nucleus into another along the way, it releases neutrinos, because those transformations are governed by the same weak force Fermi described. The sun is, among other things, an enormous neutrino factory, and it has been running for 4.5 billion years. Because neutrinos barely interact, they leave the sun with almost insulting ease. A particle of light born in the core does not fly straight out. It is absorbed and re-emitted over and over by the dense plasma, bouncing on a random path that can take tens of thousands of years to reach the surface. The neutrino suffers none of this. Born in the same fiery centre, it exits the entire sun in about 2 seconds, and then crosses the gulf to Earth in about 8 minutes, arriving fresh from the core while the light beside it is ancient. And it is not only the sun. Neutrinos come from many sources, and you are bathed in all of them at once. The rocks beneath your feet contain traces of radioactive elements, and their decays send neutrinos up through the ground. Nuclear reactors pour them out by the trillions. Far off in the galaxy, exploding stars release brief, colossal floods of them. There is even a faint sea of neutrinos left over from the Big Bang itself, cooled and stretched over billions of years, drifting through all of space, including the space your body occupies right now. Add it up, and the numbers become almost comic. In the time it takes to read this sentence, many trillions of neutrinos have passed through your body, entering from every direction, leaving no bruise, no heat, no sensation of any kind. They came through the wall behind you. They came up through the floor, having just crossed the whole Earth. You have never felt a single one, and you never will, because feeling requires touching, and touching is the one thing the neutrino almost never does. There is something humbling in this. We tend to think of our bodies as solid, and of the world as a place of surfaces and contact. The neutrino reveals how open matter really is. At the scale where neutrinos live, an atom is mostly empty space, a tiny dense nucleus with a vast hollow around it, and the neutrino threads that emptiness without incident. We are, to a neutrino, almost not there at all. The flood passes through as if we were made of gaps, which, in a sense, we are. This endless silent flood is exactly what the hunters needed. Pauli feared the neutrino could never be caught because any one of them is so unlikely to interact. But nature had supplied the other half of the equation for free, an unimaginable abundance of them, always arriving, never stopping. If you could gather enough atoms and watch them long enough under a strong enough source, the arithmetic that had seemed hopeless might just tip in your favour. Two men would decide to try, and they would begin, of all places, by considering a nuclear bomb. In the years after the Second World War, two physicists at Los Alamos decided to do the thing Pauli had called impossible. Their names were Frederick Rains and Clyde Cowan. Rains was restless after the war, looking for a problem big enough to matter, and catching the neutrino was as big as problems came. Cowan was a skilled experimenter, willing to build strange machines. Together they set out to detect a particle that a wall of lead, a light year thick, could barely stop. Their first idea tells you how boldly they were thinking. If you need an overwhelming flood of neutrinos, what is the most intense burst of them you could arrange? Their early answer was a nuclear bomb. A fission explosion releases a stupendous number of neutrinos in a fraction of a second, and Rains and Cowan seriously proposed placing a detector near a test blast, dropping it down a shaft, and catching the neutrino signal in the instant before the whole apparatus was destroyed. The plan was reviewed and remarkably not immediately dismissed. It was the kind of scheme only the early atomic age could produce. Cooler thinking prevailed, and they turned to a steadier source. A nuclear reactor does not explode, but it runs continuously, and its core pours out antineutrinos in a relentless stream, the byproducts of countless fission fragments decaying inside. A reactor could deliver a flood nearly as rich as a bomb, but for months at a time, calmly, letting the experimenters watch and wait. They gave their effort a fittingly eerie name. They called it Project Poltergeist, after the unseen spirit that makes itself known only by its effects. The detector they designed was clever in a way that turned the neutrino's weakness against it. They built large tanks filled with water and dissolved cadmium chloride into that water. Around and between the water tanks they placed liquid scintillator, a special fluid that gives off a tiny flash of light whenever a fast-charged particle races through it. The whole assembly was wrapped in sensitive light detectors, ready to catch those faint flashes. The plan was not to stop a neutrino by brute force. The plan was to arrange matter so that the rare interaction, when it finally came, would announce itself unmistakably. They needed that unmistakable signature because the enemy was noise. A detector sitting near a reactor is bombarded by all sorts of stray radiation and cosmic rays from above, any of which can make a flash of light. If they simply watched for a single flash and called it a neutrino, they would fool themselves 1,000 times over. What they needed was a signal so specific, so unlikely to be faked, that when they saw it they could trust it. The design of that signature was the heart of the whole enterprise, and it rested on exactly what happens when an antineutrino finally touches a proton. Rains and Cowan first ran their experiment in 1953 at the Hanford site in Washington, and the results were suggestive but muddied by background noise. The reactor environment was noisier than they had hoped, and the signal they saw was not clean enough to convince the world or even fully themselves. Rather than declare victory on shaky evidence, they went back, improved the shielding and the design, and looked for a better place to try again. That restraint, the willingness to doubt their own hopeful data, is part of what makes the story trustworthy. The better place was a powerful reactor at the Savannah River plant in South Carolina. There, with an improved detector buried near the reactor and shielded against the rain of cosmic rays, they set up to watch for the one specific double flash that only a neutrino could produce. To understand why that double flash was so convincing and why it finally silenced the doubters, we need to look at the exact reaction they were waiting for. The moment an antineutrino strikes a proton and leaves two separate fingerprints, spaced a few millionths of a second apart. By 1956, Rains and Cowan had their detector running beside the powerful reactor at Savannah River, buried where thick earth could screen out much of the cosmic noise from above. Night after night, the reactor poured antineutrinos through their tanks of water, and the light detectors watched for one thing: a particular pair of flashes with a particular gap of time between them. Most of what they saw was ordinary background, the random sparks of a busy world. But every so often, the exact pattern they were hunting for appeared. First one flash, then, a few millionths of a second later, a second. To be sure the pattern really came from the reactor's neutrinos, they did something simple and powerful. They compared the counts when the reactor was running to the counts when it was shut down. If the signal was truly caused by neutrinos from the reactor core, it should rise when the reactor was on and fall away when it was off. That is exactly what they found. The rate of those paired flashes climbed with the reactor running and dropped when it stopped. The signal breathed in time with the source. It was not a stray artifact, it was the neutrino answering at last. They checked and rechecked, ruling out the ways they might be fooling themselves because they knew the weight of the claim. They were saying they had caught a particle that one of the greatest physicists alive had feared was uncatchable. When they were finally confident, they did something quietly wonderful. They sent a telegram to Wolfgang Pauli, the man who had reluctantly conjured the neutrino 26 years earlier, to tell him that his ghost had been found. The message reached Pauli in Zurich. It reported that they had definitely detected neutrinos from fission fragments by observing the very reaction he had made possible, and it thanked him for the particle. Pauli, by the accounts that survive, was moved. He and some companions reportedly celebrated the news, and he sent a reply back to the team. The particle he had proposed with an apology, the one he had bet would never be seen, had been seen, and he lived to know it. He would die just 2 years later, in 1958, so the timing was a near thing. There is a poignant footnote to the honours that followed. The Nobel Prize in Physics for this discovery was awarded in 1995, nearly 40 years after the detection, and it went to Frederick Rines. Clyde Cowan was not named alongside him, for the plain and sad reason that Nobel Prizes are not given after death, and Cowan had died in 1974. 2 men had chased the ghost together. Only one lived long enough to stand in Stockholm and be thanked for catching it. What Rains and Cowan had proven was not a small thing. For a quarter of a century, the neutrino had lived entirely on paper, and in theory, a necessary invention that balanced the books but touched no instrument. Now it had left a mark in the real world, a specific, repeatable, reactor-linked signal that could not be waved away. The particle that shouldn't leave a trace had left one, faint, rare, and buried in noise, but real. And yet catching it had required a very particular piece of cleverness, the double flash that separated the true signal from the endless false ones. That signature was not an accident of the equipment. It came directly from the physics of what a neutrino does when it finally strikes a proton, a 2-step reaction that leaves 2 distinct marks a few microseconds apart. Understanding that reaction shows you not just how they caught the neutrino, but why the catch was believable at all. It is worth slowing down to see exactly how the ghost, in the one instant it touches, gives itself away twice. Everything Rains and Cowan saw rested on a single reaction, and it is worth walking through slowly. The antineutrinos streaming from the reactor passed through their tanks of water, and water is full of protons since every hydrogen atom in it carries one at its heart. Almost every antineutrino ignores every proton and flies on. But once in a great while, an antineutrino strikes a proton dead on, the weak force acts, and the proton is transformed. It becomes a neutron, and in the same instant a new particle springs out, a positron, which is the antimatter twin of the electron. This reaction has a name, inverse beta decay, because it runs the beta decay process in reverse. Now watch what those two products do, because this is where the double flash comes from. The positron, that antimatter electron, does not last long in a world made of ordinary matter. Almost immediately it meets a normal electron, and the two annihilate each other, vanishing in a puff of energy that comes out as light. That light is the first flash, born the moment the neutrino touches. It is prompt, it is sharp, and it marks the instant of the interaction. The neutron does something slower. Freed by the reaction, it wanders through the water, bumping gently from atom to atom, gradually losing speed. This is why Rains and Cowan dissolved cadmium into their water, because cadmium is hungry for neutrons. After a few millionths of a second of wandering, the neutron is captured by a cadmium nucleus, which swallows it and, in its excitement, spits out a burst of light. That is the second flash. It comes late, delayed by the neutron's slow drift, and it arrives a few microseconds after the first. There is the fingerprint, not one flash, but two, in a fixed order, separated by a fixed and characteristic gap of time. A flash from the positron, then, a few microseconds later, a flash from the captured neutron. Nothing else in that reactor environment naturally makes this exact pair with this exact spacing. A stray cosmic ray makes one flash. A bit of background radioactivity makes one flash. Only the neutrino's own two-step reaction makes the prompt flash followed by the delayed flash, like a knock at the door answered a beat later by a second knock. This is why the signal was so convincing, and why the reactor test could not be explained away. The experimenters were not looking for any flash of light, which the world produces constantly. They were looking for a specific rhythm, a coincidence so unlikely to happen by chance that when it appeared, and appeared more often with the reactor on, it could only mean one thing. They had turned the neutrino's own reaction into a signature no imposter could easily forge. The ghost, in the single instant it touched matter, left not one trace but two. And the pattern of those two traces was its confession. It is worth naming a subtlety that would matter enormously later. What the reactor produced, and what they detected, was strictly the antineutrino, the antimatter partner of Pauli's particle. In the 1950s, this distinction was barely explored, and for the purpose of proving the particle real, it hardly mattered. But the question of how neutrinos and antineutrinos differ, and whether they might in some deep sense be the same thing, would return decades later as one of the most profound puzzles in all of physics. For now, the point stood: matter had spoken. The neutrino was real. With the particle finally in hand, the natural next question was whether there was only one kind. Fermi's theory had paired the neutrino with the electron, the familiar light particle of the atom. But the electron, it turned out, had heavier cousins, and where there were heavier cousins, there might be more neutrinos too. The search for a second flavour would take the hunt out of the reactor hall and into a new kind of machine, one that could fire neutrinos in a controlled beam. The electron has a heavier relative called the muon. It behaves almost exactly like an electron, carrying the same charge and obeying the same rules, but it weighs about 200 times as much, and it is unstable, decaying in a fraction of a second. When physicists first found the muon in cosmic rays, one of them famously asked who had ordered it, because nothing in the theory demanded a heavier copy of the electron. Its existence raised a sharp question about neutrinos. When a muon is involved in a weak interaction, is the neutrino that appears the same as the one that comes with an electron, or is it a different kind? There were two possibilities, and they were cleanly opposed. Perhaps there was just one neutrino in all of nature, a single species that partnered with electrons and muons alike. or perhaps each had its own, an electron neutrino tied to the electron and a separate muon neutrino tied to the muon. The difference was not a matter of taste. It could be tested if you could make a beam of neutrinos from muon-type reactions and see what those neutrinos did when they finally interacted. In 1962, 3 physicists at Brookhaven National Laboratory in New York set out to do exactly that. Their names were Leon Lederman, Melvin Schwartz, and Jack Steinberger. They used a particle accelerator to produce a spray of particles called pions, and those pions decayed in flight into muons and neutrinos by letting the stream slam into a thick barrier of steel made partly from the armor plate of old warships. They absorbed everything except the neutrinos, which passed through untouched. On the far side, they had something new in the world, a made-to-order beam of neutrinos, all of them born alongside muons. Then they watched what those neutrinos did on the rare occasions they interacted in their detector. The logic was beautifully simple. If there was only one kind of neutrino, these beam neutrinos should sometimes make electrons and sometimes make muons when they struck, with no preference. But if the muon neutrino was its own distinct species, it should make only muons, never electrons, because it remembered the muon it was born with. The experiment would settle the question by counting which particles came out. The answer was clear. The neutrinos in the beam produced muons and essentially never produced electrons. The neutrino born with a muon made only muons when it interacted. That could only mean the muon neutrino was a separate flavour, distinct from the electron neutrino that Raines and Cowan had caught. Nature had not one neutrino, but at least 2, each tied to its own charged partner, each keeping faith with its own kind. This experiment earned Lederman, Schwartz and Steinberger the Nobel Prize in 1988. The result did something more than add a particle to the list. It revealed a hidden structure, a pattern of pairing. The electron went with the electron neutrino. The muon went with the muon neutrino. Nature seemed to be organised into matched sets, each containing a charged particle and its own private neutrino, and the weak force respected those sets. A muon neutrino kept its muon nature the way a letter keeps its address. This idea, that particles come in families, would become one of the organising principles of everything that followed. It also introduced a technique that would echo through this whole story. Raines and Cowan had waited passively for reactor neutrinos to arrive. The Brookhaven team had built a beam, deliberately manufacturing neutrinos of a chosen type and aiming them at a target. That ability, to make neutrinos on purpose and point them where you wanted, would grow into one of the most important tools in the field. It is, in fact, exactly the tool that CERN would one day use to fire neutrinos hundreds of kilometers across a continent. But before that, there was a third family member still to find, and it would prove the hardest of all to see. Nature, it turned out, was not finished at 2. In 1975, a physicist named Martin Pearl, working at the Stanford Linear Accelerator Center in California, found signs of a third charged particle in the electron family. It was heavier still than the muon, thousands of times heavier than the electron, and it was named the tau. The tau behaves like an even more massive cousin of the electron and the muon, and like them it decays quickly. Its discovery, which won Pearl a share of the Nobel Prize in 1995, immediately raised an obvious expectation. If the pattern held, and every charged particle in this family came paired with its own neutrino, then the tau should have one too. There ought to be a tau neutrino born alongside taus in weak interactions, keeping faith with the tau the way the muon neutrino kept faith with the muon. The symmetry of the picture almost demanded it. But expecting a particle and detecting one are very different things, and the tau neutrino would resist detection longer than either of its siblings. The difficulty came from the tau itself. A tau neutrino betrays its identity by making a tau when it interacts, just as a muon neutrino makes a muon. But the tau is heavy and fleetingly short-lived. To make one, the neutrino needs a large amount of energy, so you need a very energetic neutrino source. And once made, the tau travels only a minuscule distance, less than a millimeter, before it decays into other particles, leaving only the tiniest kink to track as evidence. Catching a tau neutrino meant catching that microscopic kink, the signature of a tau that lived for a whisper of time and then was gone. It took until the year 2000. At Fermilab near Chicago, an experiment called DONUT, short for direct observation of the new tau, was built to do exactly this. The team created an intense high-energy beam rich in tau neutrinos and aimed it at layered detectors filled with fine-grained emulsion, a photographic material capable of recording particle tracks with extraordinary precision, fine enough to see that sub-millimeter kink. Then they sifted through the rare interactions, looking for the telltale short track that bent, the mark of a tau appearing and instantly decaying. They found it. In a handful of interactions out of an ocean of data, the emulsion held the fingerprint of a tau neutrino, the brief straight track of a tau that travelled a fraction of a millimeter and then kinked as it fell apart. The third neutrino was confirmed, directly observed at last, 70 years after Pauli first imagined that a neutral, invisible particle might exist at all. The family was complete. 3 charged particles, the electron, the muon, and the tau, each with its own neutrino partner, the electron neutrino, the muon neutrino, and the tau neutrino. This completed a picture of remarkable order. The particles of matter arrange themselves into 3 generations, 3 repeating sets that differ mainly in mass, each set carrying a charged particle and its dedicated neutrino. Why there are exactly 3, and not 2 or 4 or 17, no one can fully say even now. It is one of the open questions that hangs over particle physics. But 3 is the number the experiments keep confirming, and the neutrinos are 1/3 of that answer, the neutral, ghostly members of each family. With all 3 flavours found, physicists could have believed the neutrino story was essentially told. They knew it was real, they knew it came in 3 kinds, and they knew it barely interacted through the weak force. It fit neatly into the grand framework being assembled, the theory that would come to be called the Standard Model. But that neat fit contained a quiet assumption, one that almost everyone made and few questioned. The neutrino was taken to have no mass at all. That assumption was about to be tested by the sun, and the sun was going to break it. By the 1970s, physicists were assembling their great achievement, a single framework that described the known particles and the forces between them. It came to be called the Standard Model, and it has since been tested to extraordinary precision. To understand what the neutrino would soon overturn, it helps to see the seat it was given in that model, and the assumption tucked into that seat. The Standard Model sorts the building blocks of matter into a tidy arrangement. There are the quarks, which clump together to make protons and neutrons, and there are the leptons, the lighter particles that stand apart, among them the electron, the muon, the tau, and their 3 neutrinos. Each force is carried by its own messenger particle. Electromagnetism is carried by the photon, the strong force is carried by particles called gluons, and the weak force, the neutrino's one companion, is carried by heavier messengers named the W and Z bosons. Those weak force messengers were themselves a triumph, and they were found at CERN. In 1983, experiments there, led in large part by Carlo Rubbia, detected the W and Z bosons directly, confirming that the weak force worked the way the theory said. This matters for our story, because it means CERN's deep involvement with the neutrinos world goes back decades. The very force that lets a neutrino interact at all is carried by particles that CERN pinned down. The laboratory now chasing the neutrino helped establish the rules of the game the neutrino plays by. Within this model, the neutrino occupies a strange and lonely position. It carries no electric charge, so the photon ignores it entirely. It feels nothing of the strong force, so the gluons pass it by. It responds only to the weak force, through those W and Z messengers, and to gravity, which for a single tiny particle is almost nothing. This is the deep reason for its ghostliness, stated in the language of the model. The neutrino is deaf to 3 of the 4 ways particles usually talk to one another. It hears only the faintest voice. There is one more feature, subtle but crucial, and it concerns a property called handedness. Particles can be thought of as spinning, and that spin can be oriented in a way physicists label left-handed or right-handed relative to the direction of motion. The weak force, strangely, is deeply lopsided about this. It interacts only with left-handed particles and right-handed antiparticles, and here is the assumption that mattered. In the original Standard Model, only left-handed neutrinos exist. There simply was no right-handed neutrino in the theory. That choice had a profound consequence. In the mathematics of the Standard Model, a particle typically gets its mass through a mechanism that requires both a left-handed and a right-handed version to exist, so they can pair up. Since the neutrino was given only a left-handed version, there was no partner for it to pair with, and so the theory naturally made it massless. The neutrino weighed nothing at all. It travelled, like the photon, at the speed of light. This was not a careless guess. It was baked into the structure of the model, elegant and consistent, and it fit every measurement anyone had. So the neutrino settled into its seat, a massless, chargeless, nearly untouchable particle that came in 3 flavours and felt only the weak force. It was a clean and beautiful picture. But cleanliness in physics is always provisional, holding only until an experiment says otherwise. The experiment that would speak was not a giant collider or a beam of manufactured particles. It was a tank of cleaning fluid at the bottom of a gold mine listening to the sun, and the number it reported would refuse, stubbornly and for decades, to match what everyone expected. We have said that neutrinos pour from the sun, but it is worth dwelling on why that makes them so precious, because it turns a nuisance into a gift. Everything else we know about the sun, we learn from its surface. The light that warms us, the spectrum that reveals its chemistry, the sunspots and flares, all of it comes from the outer layers. The core, where the actual fusion happens, is buried beneath hundreds of thousands of kilometers of dense churning plasma. We cannot see into it with light. Light cannot get out of it, not directly. Consider the journey of a single photon born in the sun's core. It does not fly outward in a clean line. The plasma is so dense that the photon travels only a tiny distance before it is absorbed by a particle, then re-emitted in some random new direction, then absorbed again, over and over, a drunken stagger through the sun's interior. By some estimates, this random walk takes tens of thousands of years before the energy finally reaches the surface and escapes as sunlight. The light that falls on your face today carries energy that left the core in an age long before human history. The neutrino makes no such journey. Born in the same core reactions, feeling almost nothing as it goes, it flies straight out of the sun in about 2 seconds and reaches Earth about 8 minutes later. It does not stagger. It does not wait. It carries news of the core as it is right now, unedited by the long climb through the plasma. If light is a letter that took thousands of years to arrive, the neutrino is a message sent live from the very centre of the star. This is why neutrinos are the only direct window into the sun's engine. Catch solar neutrinos, count them, measure their energies, and you are reading the fusion reactions in the core almost in real time, watching the furnace itself rather than the warmth that eventually leaks from its walls. No other messenger can do this. For a physicist who wants to test whether we truly understand how stars shine, solar neutrinos are the ultimate check, a way to peer through hundreds of thousands of kilometers of star as if it were glass. To use that window, though, you need to know how many neutrinos to expect. This is where an American astrophysicist named John Barkall did essential work. Over many years, Barkall built detailed theoretical models of the sun's interior, calculating the rates of the various fusion reactions, and from those, predicting exactly how many neutrinos of each energy should be streaming toward Earth. His calculations became the standard against which any measurement would be judged. If you built a detector and counted solar neutrinos, Barkall's numbers told you what the count should be. The prediction was not vague. It was a specific quantity, grounded in well-understood physics, the product of decades of careful work on how stars produce energy. Barkall was confident in it, and he had reason to be. because the underlying physics of fusion was well tested and the solar model reproduced the sun's known properties. So the stage was set for a beautiful confirmation. Build a detector sensitive to solar neutrinos, count them, compare the count to Bahcall's prediction, and watch the theory of how the sun shines pass its hardest test. That is not what happened. When the first great experiment finally counted the sun's neutrinos, the number came up short, badly short, only about a third of what Bahcall's model demanded. Not a small discrepancy to be shrugged off, but a gaping hole, 2/3 of the expected neutrinos simply missing. Something was wrong, and no one knew what. It could be the detector, it could be Bahcall's model of the sun, or it could be something about the neutrino itself that no one had yet imagined. That missing 2/3 became one of the longest-standing puzzles in physics. The experiment that opened the puzzle sat nearly 1.5 miles underground, in the Home State gold mine in South Dakota. There, beginning in the late 1960s, a chemist named Raymond Davis built one of the most patient experiments in the history of science. He filled an enormous tank, holding about 100,000 gallons, with perfluoroethylene, an ordinary dry cleaning fluid. The reason for that particular liquid was a quiet piece of chemical cleverness involving the chlorine atoms it contained. Very rarely a solar neutrino passing through the tank would strike a chlorine nucleus and, through the weak force, transform it into a nucleus of argon, a different element. This is the neutrino's touch, converting one atom into another. Argon is a noble gas, chemically aloof, so each newly made argon atom would drift free in the fluid. Davis's method was almost unbelievable in its delicacy. Every so often he would flush the entire 100,000-gallon tank and extract the mere handful of argon atoms that solar neutrinos had created inside it, then count them one by one as they slowly decayed. Think about the scale of that. In a tank the size of a swimming pool, filled with an ocean of fluid, the sun's neutrinos would produce only a few atoms of argon in a month, a few individual atoms among uncountable trillions of others. Davis developed the chemistry to sweep out those few atoms and detect them, a feat of counting so precise it is hard to overstate. The experiment ran for years, then decades, patiently tallying the sun's neutrinos a few atoms at a time. It was located deep underground for a reason, so that a mile of rock overhead could shield the tank from cosmic rays that would otherwise swamp the tiny signal. When Davis compared his count to John Bahcall's prediction, the numbers did not agree. Davis kept finding only about 1/3 of the neutrinos the solar model said should be there. 2 out of every 3 expected neutrinos were simply not showing up. This was the solar neutrino problem, and it was maddeningly stubborn. Davis and Bahcall worked as close colleagues, one measuring and one predicting, and neither could find the mistake that would close the gap. The experiment seemed sound. The solar model seemed sound. Yet the numbers stood 2/3 apart. For years, the natural assumption was that someone had simply made an error. Perhaps Davis was losing argon atoms somewhere in his elaborate extraction, undercounting the true number. Perhaps Bahcall's model of the sun's core was slightly off, over-predicting the neutrino flux. These were reasonable suspicions, and both men worked hard to test them. Davis refined his chemistry and checked his efficiency again and again. Bahcall refined his solar calculations, folding in better data about the sun. The gap did not close. The missing neutrinos stayed missing. There was a third possibility, stranger than the other two, and at first it lived only at the edges of the conversation. Perhaps nothing was wrong with the experiment or the sun at all. Perhaps the neutrinos were being produced in exactly the numbers Bahcall predicted, but something happened to them on the way to Homestake, something that made 2/3 of them invisible to Davis's chlorine. His detector was sensitive only to electron neutrinos, the flavour born in the sun. What if the neutrinos were changing into something his tank could not see? That idea was easy to say and hard to accept, because it required the neutrino to do something the standard model forbade. A massless particle, travelling at the speed of light, is frozen in a sense, unable to change its nature in flight. For neutrinos to transform on the way from the Sun, they would need mass, and mass was exactly what the theory said they did not have. To solve the solar puzzle this way meant rewriting the neutrino's place in physics. Most people were not ready for that. The problem would smoulder for 30 years before it was resolved. For roughly 30 years, the solar neutrino problem sat unresolved, and it is worth appreciating how uncomfortable that was. This was not an obscure technicality. It was a direct clash between our theory of how the Sun shines and a careful measurement of the Sun's own neutrinos, and it would not go away. Every year Davis kept counting, and every year the count stayed low. The scientific community lived with a 2/3 discrepancy in one of the most fundamental measurements it could make, and no one could say for certain where the fault lay. The doubt cut 3 ways at once. Maybe Davis was wrong, his delicate chemistry quietly losing argon atoms and undercounting. Maybe Barkall was wrong, his solar model overstating how furiously the core burned. Or maybe the neutrino was doing something no one understood. Each possibility had defenders, and each was tested with growing seriousness. The stakes rose as the years passed, because whichever answer was true, it would teach us something important, either about our instruments, our star, or our theory of matter. To check Davis's result, physicists built other detectors using entirely different methods, so that no single technique could be blamed. In Europe, an experiment called GALEX used gallium, and in Russia, an experiment called SAGE used the same element, both relying on a reaction sensitive to lower energy solar neutrinos than Davis's chlorine could catch. If Davis had simply botched his chemistry, these gallium experiments, built and run by different teams with different methods, should not reproduce his deficit. They reproduced it. They too found fewer solar neutrinos than the model predicted. The shortfall was real, and not a quirk of one tank. Another experiment, Kamiokande in Japan, took a completely different approach, using a huge tank of ultra-pure water and watching for the faint flashes of light produced when a neutrino scattered off an electron. This method could even show which direction the neutrinos came from, and it confirmed that the particles were indeed streaming from the Sun. Kamiokande also saw a deficit. From several directions, with several techniques, the answer kept coming back the same. The Sun's electron neutrinos were arriving in smaller numbers than they should. Meanwhile, Barkall's solar model was subjected to fierce scrutiny, and it held up. A separate field, heliosismology, learned to read the Sun's internal structure by studying the way its surface vibrates, the way you might study a bell by listening to its ringing. Those studies confirmed that Barkall's picture of the solar interior was accurate to remarkable precision. The core was behaving as the model said. If the Sun was producing the predicted number of neutrinos, and independent detectors were all finding too few, then attention swung slowly and reluctantly toward the third suspect, the neutrino itself. The strange explanation began to look less strange. If the electron neutrinos born in the Sun were somehow turning into muon neutrinos or tau neutrinos on their way to Earth, then detectors tuned to catch electron neutrinos would miss the transformed ones and count too few. The missing 2/3 would not be missing at all. They would be present, but wearing a different flavour, invisible to experiments looking only for the flavour they started as. It was an elegant idea, and it had actually been proposed long before, by a physicist thinking about neutrinos in a way far ahead of his time. That physicist was Bruno Pontecorvo, and his idea was that neutrinos could oscillate, changing from one flavour to another and perhaps back again as they travelled. To most of his contemporaries it had seemed a curiosity, because it demanded that neutrinos have mass, which the standard model denied. But the solar neutrino problem was now pressing so hard that the curiosity deserved a serious second look. To understand how a particle could change its very identity in flight, we have to follow Pontecorvo's reasoning, which begins with a genuinely surprising idea about what a neutrino actually is. Bruno Pontecorvo was an Italian physicist, a former student of Fermi's, who spent much of his career thinking about neutrinos more deeply than almost anyone else of his generation. As early as the late 1950s, and in more developed form through the 1960s, he proposed an idea that sounded almost like a paradox. A neutrino, he suggested, might not have a single fixed identity. It might change flavour as it travels, an electron neutrino becoming a muon neutrino, then perhaps changing back, oscillating between kinds along its path like a slow, silent pulse. To see how this is even possible, you have to let go of a hidden assumption. We have been speaking of the three flavours, electron, muon and tau, as if each is a definite solid kind of particle. Pontecorvo's insight was that flavour might not be the neutrino's most basic property. Instead, he suggested, there could be a deeper set of neutrino types defined not by flavour, but by mass. Call them mass states, and each flavour we observe is actually a blend of these mass states mixed together. The electron neutrino is one particular mixture, the muon neutrino another. Here is a comparison that helps, though like all comparisons it eventually strains. Think of a musical chord made of two notes played together. The chord is one thing you hear, but it is built from separate notes, each vibrating at its own frequency. A neutrino's flavour is like the chord, a combination, while the mass states are like the individual notes underneath. Because each note has a different frequency, the way they line up with each other shifts as time passes. The chord you hear at one moment can, a little later, sound like a different chord entirely, even though the same underlying notes are playing. Now let those underlying notes be the mass states, and let their different frequencies come from their different masses. As a neutrino flies through space, its mass states travel together but get gradually out of step with one another, because a slightly heavier mass state moves through its internal rhythm at a slightly different rate than a lighter one. The particular blend that added up to an electron neutrino at the start slowly rearranges itself, as the notes drift out of phase into a blend that looks like a muon neutrino. Travel farther, and it may drift back. The flavour pulses along the path. This is neutrino oscillation, and notice what it quietly demands. For the mass states to drift out of step, they must have different masses, and for them to have different masses, at least some of them must have mass at all. A particle with no mass has no internal rhythm to keep, nothing to drift. So Pontecorvo's oscillation, if it were real, could only happen if neutrinos were not massless after all. The very phenomenon that would explain the missing solar neutrinos carried within it a challenge to the Standard Model's neat assumption. To change flavour, the neutrino must weigh something. When Pontecorvo first proposed these ideas, they were largely a theoretical curiosity, admired for their cleverness but not urgently needed. The Standard Model with massless neutrinos fit the data of the day, and there was no compelling reason to complicate it. Pontecorvo was, in a sense, ahead of the evidence, working out the consequences of a possibility before any experiment forced the issue. His idea has the quality of a prepared answer, waiting patiently for the question the sun would eventually ask. And when that question finally grew loud enough to demand a reply, physics would have to face what oscillation really costs, a small but decisive change to one of its most successful theories. Suppose the neutrinos really do oscillate. Follow that supposition honestly, and it forces a change in the deepest description we have of matter. The original Standard Model, for all its triumphs, was built with a massless neutrino, a particle that came only in a left-handed form and therefore had no way to acquire mass through the theory's usual machinery. Oscillation says that picture is incomplete. If flavours change in flight, neutrinos have mass, and if neutrinos have mass, the Standard Model as first written is missing something real. It is worth being clear about how gentle and how serious this revision is. The Standard Model does not collapse. Nearly all of its predictions stand untouched, confirmed to breathtaking precision. What changes is one entry that had been set to 0. The neutrino's mass, long assumed to be exactly nothing, must instead be a small but genuine number. That may sound like a minor correction, nudging one value slightly upward, In physics, though, the difference between exactly zero and merely very small is enormous, because zero usually signals a deep reason, a symmetry or a rule, and a non-zero value means that reason is not there. The neutrino having any mass at all means the theory's tidy explanation for why it had none was wrong. How much mass are we talking about? The answer is part of what makes this so striking. The neutrino's mass is not just small, it is fantastically small. So small that for a long time zero seemed a perfectly good approximation. An electron, itself, a lightweight particle, is at least hundreds of thousands of times heavier than a neutrino. If you imagine the electron as having the weight of a small coin, the neutrino would weigh less than a speck of dust beside it. Oscillation experiments, importantly, do not measure this mass directly. They measure the differences between the mass states, the gaps that let the notes drift out of step, and those gaps are tiny. The neutrino is the lightest particle of matter we know by an enormous margin, and no one fully understands why it is so feather-light. That extreme lightness is itself a clue, and it points toward new physics beyond the original model. One favoured idea is that the neutrino gets its tiny mass through a mechanism unlike the one that gives other particles theirs, an idea often called the seesaw. In this picture, the very smallness of the neutrino's mass is tied to the existence of a partner particle that is fantastically heavy, so that as one goes up, the other comes down, like the two ends of a seesaw. If that is right, then the neutrino's featherweight is not an awkward accident, but a window onto physics at energies far beyond anything we can reach directly, a hint of heavy hidden particles betrayed only by how light the neutrino is. This remains a leading proposal, not a settled fact. There is a further, almost philosophical consequence hiding here, and it will return later in our story. To give the neutrino mass in the simplest way that also explains its lightness, some theories suppose the neutrino is its own antiparticle, that neutrino and antineutrino are, at the deepest level, the same thing seen from different angles. No other particle of matter is quite like this. It is a genuinely strange possibility, and whether it is true is one of the open questions physicists are working hardest to answer even now. For all this reasoning, an argument is not a demonstration. Everything so far, the missing solar neutrinos, Pontecorvo's oscillation, the demand for mass, formed a compelling case, but a case can be wrong. What physics needed was an experiment that could catch oscillation in the act, that could show the same neutrinos changing flavour, and prove that the ones missing from one type had turned into another. That proof would come from two remarkable detectors, one watching neutrinos made in the sky above, the other built to catch every flavour the sun could send. Together they would finally settle it. The proof came, in part, from a place designed to watch a different kind of neutrino entirely. Deep under a mountain in Japan sits Super-Kamiokande, an enormous tank holding 50,000 tons of ultra-pure water, its walls studded with more than 11,000 light detectors staring inward. When a neutrino interacts in that water, it can produce a charged particle moving faster than light moves through water, and that particle leaves a faint cone of blue light in its wake. From the ring of a light on the detector walls, physicists can tell what kind of neutrino passed through and which way it was going. Super-Kamiokande was watching atmospheric neutrinos, and these are worth understanding because they set up a beautiful test. High above the Earth, cosmic rays from space constantly slam into the upper atmosphere, and those collisions produce showers of particles that decay into neutrinos, mostly muon neutrinos, with some electron neutrinos mixed in. These neutrinos rain down on the whole planet from all directions at once. Some are made in the sky directly overhead and travel just a few kilometers down to the detector. Others are made on the far side of the Earth and travel all the way through the planet to reach the tank from below. Here is the elegant part. Neutrinos ignore the Earth, so both groups arrive at the detector easily. The difference between them is distance. The ones from overhead have travelled only tens of kilometres. The ones from below have travelled thousands, the full width of the Earth. If neutrinos oscillate, changing flavour over distance, then the neutrinos that came the long way through the planet should show more change than the ones that came straight down. The Earth itself becomes the ruler, letting one detector compare short journeys against long ones. In 1998, the Super-Kamiokande team announced what they had found, and it was exactly the fingerprint of oscillation. The muon neutrinos coming down from overhead arrived in the expected numbers. But the muon neutrinos coming up from below, having crossed the whole Earth, were depleted. Many of them had gone missing along the way. They had not vanished into nothing. They had oscillated into a flavour the detector was less able to see, most likely tau neutrinos, over the long journey through the planet. The amount of disappearance grew with distance, precisely as oscillation predicts. This was the first solid direct evidence that neutrinos oscillate, and therefore that they have mass. It did not come from the Sun at all, but from neutrinos born in the atmosphere, which made it a powerful independent line of attack. The solar neutrino problem and the atmospheric neutrino result were two different puzzles pointing at the same answer. Neutrinos change flavour. The announcement landed with real force in the physics community, because it was the first laboratory confirmation that the standard model's massless neutrino was wrong. The leader of the Super-Kamiokande analysis, Takaaki Kajita, would later share the Nobel Prize for this discovery. His results showed the disappearance of muon neutrinos over distance, a clear signal that they were transforming. But there was still a piece missing from the complete story. Super-Kamiokande had shown neutrinos going missing, vanishing from the flavour they started as. To fully close the case, especially for the Sun, someone needed to show the other side of the ledger, that the missing neutrinos really did reappear as other flavours, that nothing was actually lost. That final confirmation would come from Canada, from a detector built around a rare and precious substance. Where Super-Kamiokande used ordinary water and watched neutrinos disappear, the next experiment would use heavy water, a special form with an extra ingredient that let it do something no other detector could. It could count not just the electron neutrinos from the Sun, but the total of all three flavours together, and by comparing those two numbers, it would prove where the missing solar neutrinos had gone. 2,000 metres underground in a nickel mine near Sudbury, Canada, sat the Sudbury Neutrino Observatory, known as SNO. What made it extraordinary was its heart, a great acrylic sphere filled with 1,000 tons of heavy water, on loan from Canada's stockpile and worth an immense sum. Heavy water looks and pours like ordinary water, but its hydrogen atoms carry an extra neutron each, making a form of hydrogen called deuterium. That small addition gave SNO a power no ordinary water detector had. It let the observatory see all three neutrino flavours, not just one. SNO could run 3 different kinds of measurement at once. Through one type of reaction, it was sensitive only to electron neutrinos, the flavour the Sun produces. Through another type of reaction, made possible by the deuterium, it responded equally to all 3 flavours together, electron, muon, and tau, counting them as a single total without caring which was which. This was the crucial trick. SNO could measure 2 numbers, the count of electron neutrinos alone, and the count of all neutrinos combined, and then simply compare them. Think about what those 2 numbers would reveal. The Sun makes only electron neutrinos in its core. If nothing happens to them on the way to Earth, then the count of electron neutrinos and the count of all flavours should be the same, because there would be nothing but electron neutrinos to find. But if the electron neutrinos oscillate into muon and tau neutrinos during the journey, then the electron neutrino count would come up short, while the all-flavour count would still capture the full number, including the transformed ones. The gap between the 2 numbers would be the missing neutrinos, caught in their new disguise. The results, announced in stages around 2001 and 2002, were decisive. The count of electron neutrinos alone was low, only about 1/3 of what the Sun should produce, exactly the deficit Davis had seen decades earlier at Homestake. But the count of all 3 flavours combined matched John Bärcall's solar model almost perfectly. The full number of neutrinos was there, just as the theory of the shining sun had always said, 2/3 of them had simply changed flavour along the way, turning from electron neutrinos into muon and tau neutrinos that Davis's chlorine could never have seen. This was the resolution, complete and clean. The solar neutrino problem was never a failure of Davis's careful chemistry, and never a flaw in Berkold's model of the Sun. Both had been right all along. The Sun produced exactly the predicted flood of neutrinos, and Davis had accurately counted the electron neutrinos that survived as electron neutrinos. The missing 2/3 had been present the whole time, hidden in flavours the early detectors could not catch. 30 years of tension dissolved into a single satisfying picture. Nothing was lost. The neutrinos had only changed. There is a quiet vindication in this for everyone involved. Davis, who had counted a few atoms at a time for decades and been doubted for it, was right. Berkold, whose solar model had been questioned again and again, was right. Pontecorvo, whose oscillation idea had seemed a curiosity ahead of its evidence, was right. And the neutrino, long filed away as massless, turned out to carry a tiny weight after all. The director of SNO, Arthur MacDonald, would share the 2015 Nobel Prize with Kajita of Super-Kamiokande, the two of them honoured together for showing, from the sky and from the sun, that neutrinos change and therefore have mass. That prize marked a turning point. For the first time, an experiment had pushed decisively past the original standard model, revealing a crack in physics' most successful theory. What that crack opened onto is the subject of everything still ahead, and it begins with a simple, stubborn question. If the neutrino has mass, then how much, and why so absurdly little? The 2015 Nobel Prize in Physics was awarded to Takaaki Kajita and Arthur MacDonald for the discovery of neutrino oscillations, which shows that neutrinos have mass. Behind that formal sentence lies a genuine turning point in the story of physics, and it is worth stating plainly what it meant. For the first time, a clear and confirmed phenomenon had reached beyond the standard model. The neutrino, by simply having any mass at all, had shown that our most successful theory of matter was incomplete. It helps to sit with how strange it is for a theory to be wrong in this particular way. The standard model is arguably the most precisely tested theory in all of science. Its predictions for countless quantities match experiment to many decimal places, an accuracy that borders on the uncanny. And yet, it made one clean, confident statement that the neutrino has no mass, and that statement is false. This is not a case of the theory being roughly right and needing a small tune-up in its numbers. It is a case of the theory containing a definite claim that nature simply contradicts. The reason this matters so much comes back to that difference between zero and small. In the original model, the neutrino's masslessness was not an arbitrary input. It followed naturally from the structure of the theory, from the choice to include only left-handed neutrinos with no right-handed partner to pair with. A massless neutrino was what that structure produced. So when experiment shows the neutrino does have mass, it is not just correcting a number. It is telling us that the structure itself is missing a piece, that there is machinery in nature the original model did not include. What is that missing machinery? This is where honesty requires patience, because physicists do not yet fully know. Several possibilities are on the table. Perhaps there really is a right-handed neutrino, a partner never yet seen, that lets the neutrino gain mass in the ordinary way. Perhaps the neutrino gets its mass through the seesaw mechanism, tied to fantastically heavy hidden particles. Perhaps the neutrino is its own antiparticle, which would open yet another route to mass. Each of these leads somewhere different, and experiments are underway to tell them apart. The crack is real, but where exactly it leads is still being explored. There is something fitting in the neutrino being the particle that first led us past the standard model. From the very beginning it has been the awkward one, the ghost invented reluctantly, the particle that ignores nearly every force, the one that resisted detection for a quarter century. It fit into the tidy framework, but it never fit comfortably. And in the end it was this shy, nearly untouchable particle not some grand new force or exotic discovery that pointed physics toward whatever comes next. The neutrino keeps its habit of showing up where the theory is weakest, confirming that neutrinos have mass immediately sharpened a set of new questions, each one now urgent rather than academic. Exactly how much does a neutrino weigh? The oscillation experiments reveal the differences between the mass states, but not the actual mass of any one of them. Which neutrino is heaviest, and which is lightest? The ordering of the three. And above all, why is the neutrino so unimaginably light compared to every other particle of matter, lighter by a factor of at least hundreds of thousands than even the electron? That last question, the sheer smallness of the mass, is where the next chapter turns, and it has sent physicists on a difficult hunt to place the neutrino on a scale and read its weight directly. Oscillation experiments proved the neutrino has mass, but they left a frustrating gap. They measure only the differences between the mass states, the tiny gaps that let the flavors drift out of step, not the masses themselves. It is like knowing that three siblings differ in height by a few centimeters without knowing how tall any of them stands. To learn the actual weight of a neutrino, physicists needed a completely different approach, one that did not rely on oscillation at all, but instead tried to feel the neutrino's mass directly in the one place it leaves a subtle mark. That place is the very reaction where this whole story began, beta decay. Recall that in beta decay, a nucleus emits an electron and a neutrino, and the two share the released energy between them. The electron's energy can be measured with great precision. If the neutrino had no mass, the electron could, in the most extreme cases, carry away essentially all the energy, leaving almost none for the neutrino. But if the neutrino has mass, then even in the most extreme case, a little energy must always be reserved just to make the neutrino exist, because mass itself is a form of energy. That reservation shows up as a tiny shift in the maximum energy the electron can have. The effect is fantastically small, hidden in the last sliver of the electron's energy range, and reading it requires extraordinary precision. In Germany, an experiment called CERN, the Karlsruhe tritium neutrino experiment, was built to do exactly this. It uses tritium, a heavy radioactive form of hydrogen that undergoes beta decay readily, and it measures the energies of the emitted electrons with a spectrometer of remarkable size and sensitivity, a vessel large enough to walk around inside. CERN watches the very tip of the electron energy spectrum, hunting for the minuscule shortfall that a massive neutrino would impose. CERN does not measure the neutrino's mass by watching it oscillate, or by catching it in a tank. It weighs the neutrino by its absence, by the faint gap it leaves in the electron's energy. So far, the experiment has not pinned down an exact value, but it has tightened the ceiling, establishing that the neutrino's mass must be below a very small limit, less than about 1 electron volt in the units physicists use, and its measurements continue to push that ceiling lower. To put that in perspective, this makes the neutrino at least hundreds of thousands of times lighter than the electron, which is already among the lightest particles known. Try to picture that smallness. If you imagine the mass of an electron as a single grain of sand, the mass of a neutrino would be a tiny fraction of that grain, so small that treating it as nothing was, for decades, a perfectly workable approximation. It is not nothing, we now know that for certain, but it is breathtakingly close to nothing. The neutrino sits at the very bottom of the ladder of massive particles, alone, far below everything else, for reasons no one has fully explained. And that unexplained lightness is precisely what makes it so interesting. In physics, when a number comes out absurdly small for no obvious reason, it usually means a deeper mechanism is at work, something not yet in the theory. The seesaw idea, mentioned earlier, is one attempt to explain it, tying the neutrino's tiny mass to hidden particles of enormous mass. If that is right, then the neutrino's featherweight is a message from an energy scale far beyond any machine we could build, encoded in the one particle light enough to carry it. Weighing the neutrino, in other words, may be a way of glimpsing physics we cannot otherwise reach. While detectors like CERN tried to weigh the neutrino at rest, another approach had been developing in parallel, one that returned to the technique pioneered at Brookhaven decades earlier. Rather than wait for neutrinos from the sun or the atmosphere, physicists learned to manufacture intense beams of them and fire those beams across enormous distances to study oscillation under controlled conditions, and one of the grandest of these beams would be built at CERN, aimed straight through the Earth at a mountain in Italy. We have spoken of CERN as the place now chasing collider neutrinos, but its involvement with the particle runs deeper and older than that. Long before the recent detectors, CERN built one of the most ambitious neutrino beams ever made, and it did so to study oscillation directly. The project was called CERN Neutrinos to Gran Sasso, or CNGS, and its purpose was to fire a beam of Mond neutrinos from Geneva, in Switzerland, all the way to a detector buried under a mountain in Italy, 730 kilometers away. The method built on the technique first used at Brookhaven scaled up enormously. CERN's superproton synchrotron accelerated protons to high energy and smashed them into a target, producing a spray of short-lived particles called pions and kaons. Those particles were focused into a forward beam and allowed to decay in a long tunnel, and as they decayed, they gave birth to muon neutrinos, all streaming in the same direction. Everything else was absorbed by rock and shielding, leaving a clean, intense beam of muon neutrinos pointed quite deliberately at a target underground on the far side of the Alps. The aiming is the part that stops you. To send neutrinos from Geneva to the Gran Sasso laboratory in Italy, the beam could not follow the curve of the Earth's surface. It had to be aimed downward, plunging into the ground at an angle, passing thousands of meters below the surface at its deepest, and rising again to meet the detector on the other side. The neutrinos travelled straight through solid rock, through the roots of mountains, because to a neutrino that rock is barely an obstacle. Engineers had to calculate the direction with such care that a beam fired into the Earth in Switzerland would arrive precisely at a detector's location in Italy, hundreds of kilometers away, after crossing the planet's crust in a straight chord. The reason for firing neutrinos across such a distance goes back to oscillation. Flavor change unfolds over distance, so to study it you want your neutrinos to travel far before you catch them. 730 kilometers gave the muon neutrinos room to oscillate along the way. And crucially, the experiment at the far end was not merely looking for muon neutrinos to go missing, the way Super-Kamiokande had. It was after something more direct and more difficult, catching the neutrinos in their transformed state, proving that the muon neutrinos had actually turned into tau neutrinos by finding taus at the far end of the beam. This is the appearance experiment, and it is the hardest and most convincing kind. Disappearance shows neutrinos leaving a flavor. Appearance shows them arriving in a new one. If you start with a pure beam of muon neutrinos, let it travel far enough to oscillate, and then find genuine tau neutrinos in your detector, you have caught the transformation red-handed, the before and the after in the same experiment. There would be no ambiguity, no missing count to interpret. You would see the muon neutrino become the tau neutrino. The detector waiting at Gran Sasso to catch those rare taus was called Opera, and it faced a formidable task. Tau neutrinos are the hardest flavour to detect, as we saw with donut, because the tau they produce travels less than a millimetre before decaying, leaving only a microscopic kink to track. To find a handful of such events, hidden in an enormous detector, produced by neutrinos that had travelled 730 kilometres through the Earth, would test the very limits of experimental patience. Opera was built to do it, and when it finally succeeded, it caught oscillation in the most direct way anyone ever had, though along the way it would also stumble into one of the most famous false alarms in the history of physics. The Opera detector at Gran Sasso was a marvel of patience and scale. To catch the microscopic kink of a decaying tau, it used the same precise technology as donut, photographic emulsion, layered with sheets of lead into building blocks called bricks. The full detector held about 150,000 of these bricks, an enormous wall of lead and emulsion waiting in the path of the beam from CERN. When a neutrino interacted inside a brick, the emulsion recorded the tracks of the particles produced, with enough resolution to reveal a tau that travelled a fraction of a millimetre before it decayed. The task was to find, in that vast assembly, the rare event where a muon neutrino from the beam had oscillated into a tau neutrino and produced a tau on impact. This required almost inhuman selectivity. The beam sent countless neutrinos through the detector, the great majority still muon neutrinos, most passing through without a trace. Only occasionally would one have oscillated into a tau neutrino, and only occasionally would that tau neutrino interact and leave its telltale kink. When electronic sensors flagged that something had happened in a particular brick, that brick was removed, its emulsion developed and scanned under microscopes, and the tracks reconstructed in search of the signature. In 2010, Opera announced its first catch. In one brick, amid the tangle of tracks, they found the fingerprint of a tau, a short track that kinked as the tau decayed. Born from a neutrino that had left CERN as a muon neutrino and arrived as a tau neutrino. It was the first time anyone had watched a neutrino appear in a new flavour at the far end of a beam, the transformation caught in the act rather than inferred from a missing count. Over the following years, Opera found more, building up a small collection of these tau appearance events, 5 in total by 2015, enough to make the result solid. This was oscillation confirmed in its most direct and satisfying form. Super-Kamiokande and SNO had shown neutrinos disappearing from one flavour and, in SNO's case, the total being conserved. Opera completed the picture by showing the actual arrival, a beam that began as muon neutrinos delivering genuine tau neutrinos hundreds of kilometres away. Start with one flavour, travel across a continent, end with another. The chord had audibly changed its notes, and Opera had recorded the new chord directly. It stands as one of the cleanest demonstrations of what the neutrino does. The achievement deserves to be remembered on its own terms, because Opera is far better known for something else, something that had nothing to do with its real scientific purpose. In the autumn of 2011, in the middle of its careful tail hunt, the Opera collaboration reported a measurement so startling that it made headlines around the world and briefly seemed to threaten the foundations of physics itself. They had measured how fast the neutrinos travelled from CERN to Gran Sasso, and the number they got appeared to be impossible. The neutrinos, according to their timing, had arrived slightly early, as if they had travelled faster than light, just 60 billionths of a second early over that 730-kilometre journey. But if real, it would have shattered a cornerstone of modern physics, Einstein's rule that nothing outraces light. The claim spread instantly and widely, and it put the Opera team in an extraordinary and uncomfortable position. They did not believe it themselves, not really, and the way they chose to handle it says a great deal about how science is supposed to work when a result seems too strange to be true. In September of 2011, the Opera collaboration did something unusual. They had a measurement they could not explain and did not trust, and rather than bury it or quietly announce a revolution, they presented it openly and asked the world to help them find their mistake. Their timing data showed the neutrinos from CERN arriving at Gran Sasso about 60 nanoseconds earlier than light would, which over the 730-kilometre path meant the neutrinos appeared to have outrun light by a small margin. The team stated plainly that they had checked and rechecked and could not find an error, and they invited scrutiny. The reaction was immediate and enormous. A faster-than-light particle would overturn special relativity, the theory Einstein published in 1905, which has underpinned physics for over a century and passed every test put to it. The idea that neutrinos of all things might break that rule captured the public imagination and set physicists everywhere to work. Most were deeply skeptical, and for good reason. Relativity's speed limit is woven into the entire fabric of modern physics, and a vast body of evidence supports it. When one measurement contradicts a mountain of confirmed theory, the smart bet is that the measurement is flawed. Still, skepticism is not the same as dismissal, and the beauty of what followed is that no one simply waved the result away. Teams around the world examined the opera setup, scrutinized the timing chain, and looked for the subtle error that must be hiding somewhere. The measurement was fiendishly delicate. It required knowing the distance between 2,730 kilometers apart to within a few meters, and synchronizing clocks at each end to within billionths of a second, using signals from GPS satellites. In a chain that intricate, there were many places a tiny flaw could creep in. By early 2012, the Opera team had found the trouble, and it was humbling in its ordinariness. There were two problems in their timing system. One was a fiber optic cable, carrying a GPS signal that had not been fully screwed into its connector, introducing a small delay. The other was a clock oscillating slightly off its intended rate. Together, these accounted for the anomaly. When the faults were corrected, the neutrino's measured speed fell back in line with the speed of light, exactly as relativity demanded. Independent measurements using the same beam soon confirmed that the neutrinos travelled at the expected speed. There is a real lesson in how this unfolded, and it is not a lesson about failure. The opera team made an error, as experimenters sometimes do in measurements at the very edge of precision, but they handled it in the way science is meant to work. They did not hide an uncomfortable result, nor did they trumpet it as a discovery. They reported it honestly, flagged their own doubt, and opened it to the scrutiny of others, and the process corrected itself within months. The system worked, precisely because no single group had the final word, and the claim had to survive the checking of everyone else. It is worth holding this calm view of a moment that was, at the time, treated as high drama. A cornerstone of physics was not overturned. A cable was loose. The neutrinos, it turned out, obey the speed limit like everything else, and opera's genuine achievement, the direct detection of tau neutrino appearance, stands untouched by the episode that made it famous. Yet the whole affair is a reminder of how hard these measurements are, and of just how difficult the tau flavor in particular is to work with. That difficulty is not incidental. The tau neutrino is genuinely the hardest of the three to catch, and understanding why sets up the final act of this story, where CERN goes hunting for neutrinos in the one place they had never been caught. Of the three neutrino flavors, the tau neutrino is by far the hardest to catch, and its difficulty is worth understanding, because it shapes what the newest experiments can and cannot do. The electron neutrino and the muon neutrino have each been detected in many settings, from reactors to beams to the sun. The tau neutrino has been directly observed only a handful of times in all of history, first by Donut at Fermilab, and then by Opera at Gran Sasso. Everything about it conspires to make it rare and fleeting. The first obstacle is energy. A neutrino reveals its flavour by the charged particle it produces when it interacts. An electron neutrino makes an electron, a muon neutrino makes a muon, and a tau neutrino makes a tau. But the tau is heavy, thousands of times heavier than the electron. To conjure one into existence, the neutrino must carry a large amount of energy, enough to pay for the tau's substantial mass. Low-energy tau neutrinos simply cannot make a tau at all, so they interact in ways that do not betray their flavour. Only high-energy tau neutrinos can produce the signature that identifies them, which means you need an energetic source to see them clearly. The second obstacle is the tau's brief life. Once a tau is finally made, it does not linger. It decays almost instantly, travelling a distance often less than a millimetre before falling apart into other particles. To prove a tau neutrino was there, you have to catch that minuscule track, the short segment where the tau existed and the kink where it decayed. This is why both Donut and Opera relied on photographic emulsion, the one technology fine-grained enough to resolve such tiny features. Ordinary electronic detectors, with their coarser resolution, usually cannot see a track that short. Put these two obstacles together and you see the bind. To detect tau neutrinos, you need them at high energy, and high-energy neutrinos are harder to produce in large numbers. You also need a detector fine enough to catch a sub-millimetre track, which limits the kinds of instruments you can use. The tau neutrino sits at the intersection of these difficulties, demanding both a powerful source and an exquisitely precise detector at the same time. It is the flavour that most tests the limits of what experimenters can build. This difficulty is not just a technical footnote. It means our knowledge of the tau neutrino remains the thinnest of the three, the least measured, the least understood. Many of its properties are known far less precisely than those of its lighter siblings, simply because we have caught so few of them. If there are surprises hidden in the neutrino sector, unexpected behaviours that do not fit the current picture, the tau neutrino is a natural place for them to hide, precisely because we have looked at it the least. The gaps in our knowledge cluster around the flavour hardest to see. All of this points toward a need, a source that produces neutrinos at very high energies, in enormous numbers, including tau neutrinos, so that this least understood flavour can finally be studied properly. And there is such a source, one that has been running for years, pouring out neutrinos of all three flavours at energies higher than almost any other, and yet whose neutrinos had never once been directly detected. That source is a particle collider. The most powerful collider ever built at CERN had been making a flood of high-energy neutrinos all along, and until very recently not a single one had ever been caught. Here is a fact that sounds almost like an oversight. Particle colliders produce neutrinos in staggering numbers at some of the highest energies achievable in a laboratory, and yet in decades of collider physics, not one of those neutrinos had ever been directly detected. The most powerful collider in the world, CERN's Large Hadron Collider, had been generating an intense flood of high-energy neutrinos with every run, and they had all streamed away uncaught, ignored, invisible. The particle whose whole story is about being hard to catch had been slipping past the world's greatest physics machine unnoticed. To see how this came about, picture what happens inside the Large Hadron Collider. It accelerates protons to nearly the speed of light and smashes them together at 4 points around its ring, where enormous detectors like ATLAS study the debris. Those collisions produce a spray of particles, and many of them, particularly short-lived ones flying forward along the beam direction, decay into neutrinos. Because the collisions are so energetic, these neutrinos are born at very high energies, higher than those in most neutrino beams, including plenty of tau neutrinos alongside the electron and muon kinds. The collider is, incidentally, a first-rate neutrino factory. So why had no one caught them? The answer lies in where the neutrinos go. They come flying out of the collision point along the beamline, in the forward direction, hugging the path of the original protons. But the great detectors like ATLAS are built to catch particles flying out to the sides, at angles from the collision, and they have a hole along the beam axis where the beam pipe passes through. The neutrinos, travelling straight ahead, escape through that gap and continue down the tunnel, missing the main detector entirely. And even if they hit it, a giant detector optimised for other particles is poorly suited to identifying the rare, faint interaction of a neutrino. There was another problem too. Right at the collision point, the neutrinos would be buried in an overwhelming blast of other particles, an explosion of debris that would drown out their whisper-faint signal. To catch a neutrino, you need quiet, a place shielded from the roar, where the only things that can reach you are the particles that pass through matter untouched. Standing right at the collision would be like trying to hear a pin drop inside a fireworks display. The neutrinos were there in abundance, but the noise made them impossible to pick out. The solution to both problems turned out to be elegantly simple. Move away from the collision, straight down the beamline, and put your detector far enough along the tunnel that hundreds of meters of solid rock stand between it and the collision point. That rock would absorb the fireworks, stopping nearly every kind of particle. Nearly every kind, but not neutrinos, which would pass through the rock as easily as they pass through everything else. On the far side, in the quiet, a small detector placed exactly on the line of sight to the collision could catch the neutrinos as they emerged, filtered clean by the very rock that blocked everything else. This was the insight behind a new experiment, small and clever, tucked into a side tunnel far from the main hall. It did not need to be huge, because the collider's neutrino flood was so intense that even a compact detector placed correctly would catch a meaningful number. It only needed to be in the right place, on the line of sight, behind enough rock to silence the noise. The idea had been proposed years earlier, and it finally took shape as a modest detector with a fitting name, one that pointed straight ahead into the forward darkness where the neutrinos flew. It was called FASER, and it was about to catch what no collider ever had. FASER, the forward search experiment, is almost comically modest next to its giant neighbours. Where Atlas stands several stories tall and weighs thousands of tons, FASER is about a ton, small enough to fit neatly into a narrow side tunnel. It sits in a service tunnel called TI-12, about 480 metres down the beamline from the point where protons collide inside Atlas. Between the collision point and FASER lies around 100 metres of rock, the natural shield that absorbs the debris of the collisions and lets only the most penetrating particles through. FASER waits in that quiet, directly on the line of sight to the collisions. The experiment came together quickly and cheaply by the standards of big physics, built in just a few years, partly from spare components borrowed from other experiments, and installed in a tunnel that had been sitting unused. It was a lean project, driven by a simple realization that the collider had been making detectable neutrinos all along, and no one had put a detector in the right spot to catch them. Physicists including Jonathan Feng, who helped initiate the project, and Jamie Boyd, who served as a spokesperson, championed the idea of a small forward detector to seize an opportunity that had been overlooked for decades. At the heart of FASER's neutrino hunt is a subdetector called FASER, built from the same principle that caught tau neutrinos before, emulsion layered with dense metal. It stacks hundreds of thin sheets of photographic emulsion between plates of tungsten, one of the densest metals available, building up a target with a mass of over a ton in a compact volume. The tungsten gives the neutrinos enough material to occasionally interact in, and the emulsion records the resulting particle tracks with the fine resolution needed to identify what kind of neutrino it was. The whole thing sits squarely on the collision axis, where the neutrino flux is richest. The logic is a direct descendant of everything that came before. FASER cannot force a neutrino to interact any more than Rains and Cowan could. What it can do is place a dense, finely instrumented target in the path of an extraordinarily intense beam of high-energy neutrinos, the beam the collider produces for free, and wait for the rare interactions to accumulate. Because the collider's neutrino flux in the forward direction is so enormous, even a compact detector like FASER catches a meaningful number over a run. Rarity times abundance, the same arithmetic that has run through this entire story, tips once again in the hunter's favour. There is a real elegance in how the whole arrangement works together. The collision makes the neutrinos. The magnets of the collider sweep away the charged particles that would otherwise cause confusion, bending them off course. The rock absorbs the rest of the debris, the electromagnetic and strong interacting particles that cannot penetrate it. What survives that gauntlet to reach FASER cleanly is essentially only neutrinos and muons, and the muons can be identified and accounted for. The neutrinos arrive filtered and quiet, exactly as the design intended, ready to be caught in the emulsion. FASER was installed and began taking data when the Large Hadron Collider started up again in 2022 for its third major run. Alongside it, on the other side of the collision point, sat a companion experiment called SNLHC, designed with the same goal using a somewhat different detector. Two small forward detectors, on either side of the collision, both aimed at catching the neutrinos that decades of collider physics had let slip away. The stage was set for a first, and it did not take long. Within its first year of data, FASER would announce something no experiment in the history of particle colliders had ever managed to report. In March of 2023, at a physics conference in Italy, the FASER collaboration announced the first direct detection of neutrinos produced at a particle collider. For the first time in the decades-long history of colliders, the neutrinos those machines had always made were no longer slipping away unseen. FASER had caught them, a clear signal of muon-neutrino interactions standing out cleanly against almost no background. Shortly afterward, the companion experiment SNDL-HC confirmed the achievement from the other side of the collision point. Collider neutrinos had finally been detected. The result carried a special weight because of what these neutrinos were. They were among the highest energy neutrinos ever produced and detected in a laboratory, reaching into an energy range that had never before been directly probed with neutrinos made by human machines. For years, neutrino interactions had been measured at lower energies, from reactors, from beams, from the sun and atmosphere, but there was a gap at the highest energies where no laboratory measurement existed. FASER's neutrinos fell squarely into part of that gap, opening a window on how neutrinos behave at energies previously beyond reach in a controlled setting. There is a fitting echo in this moment, reaching back to the very beginning of the story. The neutrino was co-discovered by Frederick Rainey nearly 70 years earlier, when he and Cowan first caught reactor antineutrinos. Now, at CERN, physicists had caught neutrinos from an entirely new kind of source, the most powerful collider ever built, closing a loop that ran from a modest reactor experiment in the 1950s to the frontier of high-energy physics. The same particle, the same fundamental challenge of catching something that barely interacts, met again with new tools at a new scale. As FASER continued running through the collider's third major run, it accumulated far more than that first handful of events, and it began to do more than simply detect. With larger data sets, the collaboration reported the first observation of electron-neutrino interactions in its electronic detector at high significance, and made measurements of how neutrino interaction rates change with energy, the kind of quantitative study that turns a first detection into real physics. The experiment operated with high efficiency, gathering hundreds of inverse femtobars of collision data, the units physicists use to measure how much collision exposure a detector has collected. Each run added to the store of high-energy neutrino events. What makes this a beginning rather than an end is the scope of what these detectors can now study. They can measure the interaction rates of all three flavors at high energy, testing whether neutrinos behave as the standard model predicts in a regime never before checked. They can look for subtle differences that might hint at new physics, and because the collider produces tau neutrinos too, these forward experiments offer a rare chance to study the hardest flavor at high energy, in a setting built to catch it. The particle that most resists detection is now being caught, run after run, in a tunnel at CERN. This is the heart of the title's promise, and it is worth stating plainly. CERN really is chasing a particle that shouldn't leave a trace, and in a specific, concrete sense it has now caught it, where no one had before. The neutrinos were always there, flooding out of every collision, ignored for decades because catching them seemed either impossible or pointless. A small detector, placed with care in the quiet behind a wall of rock, turned that flood into data. And this is only the first of what physicists expect to be many results, because the questions these high-energy neutrinos can help answer are among the deepest still open. Why does it matter to measure neutrinos at these very high energies, in a range never before reached in a laboratory? The answer is that every energy regime is a fresh test of whether we truly understand the particle. The standard model, updated to include neutrino mass, makes specific predictions about how often neutrinos should interact at a given energy, how their interaction rate climbs as energy rises. Those predictions had been checked at lower energies, but the highest energies were unexplored territory. Firm measurements there could confirm the theory, or reveal a crack where something new is hiding. There is a practical reason this range had stayed dark. Making neutrinos at very high energy is difficult, and the collider does it almost as a byproduct, flinging out energetic neutrinos in the forward direction as a free consequence of its collisions. Before FASER and SNDL-HC, no one had a detector position to catch them, so the energy range between the reach of ordinary neutrino beams and the realm of cosmic neutrinos from space sat empty of laboratory data. The forward detectors at CERN began, for the first time, to fill that emptiness with real measurements made under controlled conditions. Filling that gap connects to something beyond the laboratory, up in the sky. High-energy neutrinos arrive at Earth from deep space, produced by violent cosmic events, distant exploding stars and the environments around black holes, and detected by huge observatories buried in Antarctic ice. Those cosmic neutrinos carry information about the most extreme places in the universe, but to interpret what they tell us, we need to know how neutrinos interact at high energies. Measuring that at CERN, where the energy is known and controlled, helps us read the messages from cosmic neutrinos whose origins we cannot control. The collider becomes a calibration for the cosmos. There is also the matter of the flavors themselves. Because the collider produces all three kinds of neutrino at high energy, the forward experiments can compare how electron, muon and tau neutrinos each interact in a regime never tested this way. If all three behave exactly as the theory predicts, that is a strong confirmation of the standard model in new territory. If one of them deviates, if the tau neutrino in particular does something unexpected, that could be the first hint of physics beyond what we know, precisely in the flavor we understand least. Either outcome teaches us something we could not have learned any other way. Looking ahead, physicists are already planning to expand this frontier. There are proposals for a dedicated facility at CERN, sometimes called the Forward Physics Facility, a purpose-built underground space to house a suite of larger, more capable forward detectors for future collider runs. Where FASER was assembled quickly and modestly from spare parts in an existing tunnel, its successors could be designed from the ground up to catch far more neutrinos, measure their properties in far greater detail, and push the study of high-energy collider neutrinos into a mature science. The first detection was the opening, not the conclusion. So the chase that gives this story its title is genuinely underway and genuinely new, but catching collider neutrinos, remarkable as it is, does not answer the deepest questions the neutrino still poses. Those questions reach beyond how often it interacts, or how it behaves at high energy, down to what the particle fundamentally is. Two puzzles in particular stand out. Questions so basic that answering them could reshape our understanding of matter itself. The first asks whether the neutrino might be its own antiparticle, a property no other particle of matter possesses, and it turns out that answering it might explain something as large as why the universe contains anything at all. Here is one of the strangest open questions about the neutrino, and it is genuinely unsettled, so it is worth stating carefully. For every particle of matter, there is a corresponding antiparticle, an opposite twin. The electron has the positron, its antimatter counterpart with opposite charge. When a particle meets its antiparticle, they annihilate. For most particles, the particle and antiparticle are clearly distinct, told apart by their opposite electric charges. But the neutrino has no electric charge, and that opens a peculiar possibility. Perhaps for the neutrino alone among matter particles, there is no real difference between particle and antiparticle. Perhaps they are the same thing. This idea traces back to the physicist Ettore Majorana, who in the 1930s worked out the mathematics of a particle that could be its own antiparticle, before he mysteriously vanished without a trace, an unsolved disappearance that has haunted physics ever since. A particle of the kind he described is now called a Majorana particle. The question for the neutrino is whether it is a Majorana particle, identical to its own antiparticle, or whether neutrino and antineutrino are truly distinct, in which case it is what physicists call a Dirac particle. No one yet knows which it is, and the answer matters enormously. How could you possibly tell? The key lies in a rare nuclear process. Certain atomic nuclei undergo a form of decay in which two neutrons simultaneously turn into two protons, emitting two electrons and two antineutrinos at once, a process called double beta decay, which has been observed and is well understood. But if the neutrino is its own antiparticle, then a stranger version becomes possible. The two antineutrinos could effectively cancel each other out, one absorbed as the other is emitted, leaving a decay that produces two electrons and no neutrinos at all. This is called neutrinoless double beta decay, and it has never been observed. If neutrinoless double beta decay were ever seen, it would be a landmark. It would prove that the neutrino is its own antiparticle, a Majorana particle, resolving a question open for decades. It would also, as a bonus, give information about the neutrino's absolute mass, the very quantity Katrin pursues by a different route. So experiments around the world are hunting for this decay, building detectors of extraordinary sensitivity, watching large quantities of specific isotopes for the faintest sign of a decay that emits 2 electrons and nothing else. So far, no one has seen it. The searchers continue, pushing their sensitivity ever higher, and the question stays open. The reason physicists care so intensely goes far beyond bookkeeping about the neutrino's nature. If the neutrino is its own antiparticle, it opens a door to explaining one of the greatest mysteries in all of science: why the universe is made of matter at all. This connects the shy, nearly untouchable neutrino to the largest question we can ask about existence, the question of why there is something rather than nothing, or more precisely, why there is something made of matter rather than a universe that annihilated itself away long ago. That connection runs through the earliest moments of the universe, and a subtle imbalance that must have existed then. It is a story that takes the neutrino from the laboratory to the birth of the cosmos, and it suggests that this faint particle, so hard to catch that its inventor apologized for it, may hold part of the answer to why the stars, the planets, and we ourselves exist. To see how, we have to look at what happened to matter and antimatter in the first instance after everything began. The universe presents us with a deep puzzle, and the neutrino may be part of its solution. According to our best understanding, the early universe should have produced matter and antimatter in equal amounts. Energy converting into particles tends to make them in balanced pairs, a particle and its antiparticle together. But matter and antimatter annihilate on contact, turning back into energy. So if the early universe made them in perfectly equal amounts, they should have almost entirely annihilated one another, leaving a cosmos of light and almost no matter at all. There would be no stars, no planets, no people. Yet here we are, in a universe full of matter with essentially no antimatter to be found. Something must have tipped the balance, ever so slightly, in the first moments after the beginning, leaving a tiny excess of matter that survived the great annihilation. For every billion or so antimatter particles, there must have been about 1,000,000,001 matter particles, and that one leftover part in 1,000,000,000 became everything we see, all the galaxies and stars and worlds. What caused that imbalance is one of the largest unanswered questions in physics, and the neutrino offers one of the most promising paths toward an answer. The path runs through a property called charge parity violation, or CP violation, which is a measure of whether matter and antimatter behave in subtly different ways. If particles and antiparticles were perfect mirror images in every respect, there would be no way to prefer one over the other, and the early universe's balance could not have tipped. But if there is some asymmetry, some way in which matter and antimatter play by slightly different rules, that asymmetry could be the seed of the imbalance. Physicists have found small amounts of CP violation among certain particles already, but not enough to explain the matter of the universe. The neutrino is a prime suspect for hiding more. Neutrinos could show CP violation through their oscillations. If neutrinos oscillate from one flavor to another at a slightly different rate than antineutrinos oscillate in the mirror image way, that difference would be a form of CP violation in the neutrino sector, and it might be substantial. Combined with the possibility that the neutrino is its own antiparticle, this could, through mechanisms physicists have proposed, help explain how the early universe came to favour matter over antimatter. The faint particle that barely interacts might carry the imprint of the asymmetry that let the universe exist. This is a leading idea under active investigation, not an established fact. To test it, physicists are building enormous new experiments, the next generation of neutrino observatories. In the United States, the deep underground neutrino experiment called DUNE will fire an intense beam of neutrinos more than 1,000 kilometers through the Earth to giant detectors filled with liquid argon, comparing how neutrinos and antineutrinos oscillate to search for a difference. In Japan, the Super-Kamiokande experiment, a vastly larger successor to Super-Kamiokande, will pursue the same question with a colossal tank of water. Both are designed to measure neutrino oscillation, with enough precision to detect CP violation if it is there. These experiments represent the frontier of the chase, and they aim the neutrino story at the biggest target of all. What began as a bookkeeping fix for a decaying atom now reaches toward the origin of matter itself. If DUNE and Super-Kamiokande find that neutrinos and antineutrinos behave differently, it would be a monumental clue to why the universe is made of something rather than nothing. The particle Pauli invented in apology may turn out to be tangled up in the reason there is a universe here to apologize in. And yet, even with all this, the neutrino has not finished surprising us, because there are hints that a fourth, even more elusive kind may exist. Even after everything we have traced, the neutrino may still be hiding something, and the hints come from small anomalies at the edges of our experiments. Over the years, a few results have not quite fit the picture of 3 neutrino flavors oscillating among themselves. Certain short-distance experiments have seen slightly more or fewer neutrinos than 3 flavors alone can explain, small discrepancies that refuse to fully resolve. These anomalies are not conclusive, and some may yet turn out to be experimental quirks, but they have kept alive a tantalizing possibility that there is a 4th kind of neutrino, even more elusive than the 3 we know. This hypothetical 4th neutrino is called the sterile neutrino, and its name captures what makes it so strange. The 3 known neutrinos are already nearly untouchable, feeling only the weak force and gravity. The sterile neutrino would feel even less. It would not respond to the weak force at all, interacting only through gravity, the faintest force of all. That would make it the ultimate ghost, a particle that ignores every force except the one that barely moves it, passing through matter with even more perfect indifference than the neutrinos we have spent this whole story learning to catch. How could such a thing ever be detected if it interacts through gravity alone? The answer is oscillation, the same phenomenon that revealed the mass of the ordinary neutrinos. Even though a sterile neutrino would not interact directly in any detector, the 3 known neutrinos might oscillate into it and back, and that mixing would leave a mark. Ordinary neutrinos would appear to go missing at rates that 3-flavor oscillation cannot explain, disappearing partly into the sterile state before returning. So physicists hunt for the sterile neutrino indirectly, by looking for anomalies in how the known neutrinos oscillate over short distances, searching for the fingerprint of a hidden 4th partner. The stakes are high, because a sterile neutrino would be physics beyond the standard model in a dramatic way. A genuinely new particle unlike anything in the current framework. It could also connect to other mysteries. Some have wondered whether sterile neutrinos, if they exist with the right properties, might make up part of the universe's dark matter, the unseen substance whose gravity shapes galaxies but which emits no light and has never been directly identified. A particle that interacts only through gravity is, after all, exactly the kind of thing dark matter might be. These connections remain speculative, but they show why the search matters. For now, the sterile neutrino remains unconfirmed and genuinely uncertain. Several experiments have been built specifically to test the anomalies, to confirm or rule out the 4th neutrino, and the evidence so far is mixed, with some results pointing toward it and others pushing against it. This is science in its unsettled state, honest about what it does not yet know. The sterile neutrino might be real, a discovery waiting to happen, or the anomalies might dissolve under closer scrutiny, leaving 3 flavors as the whole story. We do not yet know which, and it would be wrong to pretend otherwise. What is certain is that the neutrino continues to sit at the edge of the known, the particle most likely to reveal the next surprise. It has done so before, breaking the standard model open by having mass, and it may do so again. From Pauli's reluctant invention to the sterile neutrino's uncertain hints, the pattern holds. The neutrino keeps appearing wherever our understanding runs out, a faint and persistent messenger from just beyond the boundary of what we know, and with that, we can return to where we began and answer, in the simplest words, the question this whole story was built to explore. Let us return to the beginning, to your hand held up to the light, with 100 trillion neutrinos passing through it every second and never once touching it. We can now say what that means with real understanding. Those neutrinos ignore your hand because they feel only the weak force, the faintest of the forces that shape matter, and the weak force acts so rarely and over such tiny distances that a neutrino can cross an entire planet or a light year of lead and almost never interact. That is why they leave no trace, not because they are magical, but because the one door through which they can touch our world is almost always shut. And yet the whole arc of this story is the arc of a particle that shouldn't leave a trace being caught anyway, again and again by patience and cleverness. Pauli invented it in apology, certain it could never be found. Rains and Cowan found it beside a reactor by watching for a double flash of light. The 3 flavours were caught one by one, the last of them, the tau, only at the turn of this century. The sun's missing neutrinos revealed that the particle changes flavour and therefore has mass, breaking the tidy theory that had no place for such a thing. And most recently at CERN, neutrinos from the world's most powerful collider were detected for the first time, the highest energy laboratory neutrinos ever caught, in a small detector waiting quietly behind a wall of rock. So the answer to the title's question is this: CERN is chasing a particle that shouldn't leave a trace, and it is catching it, because rarity is not the same as impossibility. Any single neutrino is almost certain to pass through untouched, but the universe supplies them in such unimaginable abundance, and physicists have learned to gather so many atoms in their path and watch so patiently that the rare touch becomes a signal you can count. The ghost is real, and it can be caught, one faint interaction at a time. Think for a moment about what this particle has given us. It has let us see into the living core of the sun, reading the fusion happening right now beneath hundreds of thousands of kilometers of plasma that light itself cannot escape. It has shown us the first crack beyond our deepest theory of matter. It may hold the reason the universe is made of something rather than nothing, the tiny imbalance that let matter survive the annihilation of the early cosmos. And it may yet reveal a fourth, even more hidden kind, or connect to the dark matter that shapes the galaxies. For a particle that barely interacts, it has an extraordinary reach. There is something worth carrying in all of this, beyond the physics. The neutrino is a reminder that the world is full of things we cannot feel and mostly do not notice, and that the invisible can be understood, patiently, honestly, without ever needing to be seen directly in the ordinary sense. It took nearly a century from a reluctant letter to a detector in a tunnel under Geneva to learn to hear this quietest of particles. That is not a story of sudden genius. It is a story of steady work, of doubting your own results, of building the right instrument and waiting. Right now, as you finish this, the neutrinos are still passing through you, streaming from the sun overhead and up through the earth beneath you, trillions upon trillions, silent and constant as they have your whole life. They connect you to the core of a star, to the birth of the universe, to the deepest open questions in physics, and they ask nothing and disturb nothing as they go. The particle that shouldn't leave a trace runs through everything, including you, and we are only beginning to learn how to listen.